Hello everyone, I'm Alka Jankit from IIT Kanpur. I'm your TA for Nature and Properties of Materials, and this week we'll be studying about atomic bonding and crystal structure. And this course is offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering and IIT Kanpur. So firstly we'll be going through some sample exam assignment questions. So our first question is the effective number of lattice points in the unit cell of simple cubic, body-centered cubic and face-centered cubic space lattices respectively are. And four options are given here. So first is 1, 2, 2, second is 1, 2, 4, and third option is 2, 3, 4, and another option is 2, 4, 4. So what should be the correct answer? So answer will be B, 1, 2, 4, and it can be explained by calculating these numbers. So someone has joined. Okay, so answer will be 1, 2, 4. And this can be calculated for simple cubic structure. You will be having atoms at the corners of all unit cell, and it will have 8 corners, and one unit cell will be one corner atom will be shared by 8 other unit cells. So effective number will be 1. So 1 atom per unit cell. And for body centered it will be similar to simple cubic, but 1 atom will be at the body center. So it will have 2 atoms per unit cell. And for face centered cubic, you will have 1 atom similar to simple cubic plus another atoms which will be at face centers, and these face center atoms will be shared with one another unit cell. So effective number will be 4 atoms per unit cell. Second question is, so who is present here? So can you please mute yourself when you're not asking question? Thank you. You can unmute yourself when you want to ask any question, okay? So second question is the coordination number for FCC crystal structure is. So your options are 4, 8, 12 and 16. So answer will be 12. So explanation, it can be explained by saying that coordination number can be defined by nearest neighbors in a crystal structure lattice. So the coordination number for FCC and HCP, these both have 12. So it can be seen from this figure. So for example, if we take this atom, so in one plane it has 6 nearest neighbors, and on top and bottom planes it has 3 other atoms. So it will be having total 12 number. And in case of FCC it will have different stacking sequence, but it will have same 12 coordination number. In case of BCC, when we see at the body center, that atom will have all corner atoms as nearest neighbors. So it will have 8 coordination number. Now third question. So you can try and solve in chat box also. If you know the answer, you can write in chat box, and if you have any query, you can ask by unmuting yourself. Okay, so next question is, a family of Miller direction is always represented as. So it either small brackets or curly bracket, triangular bracket or square brackets. So what will be the answer? Answer will be triangular bracket, and for it can be explained by saying that in case of a direction it is denoted as square bracket, and family will be denoted as triangular bracket. So this family will have various directions in it, and a plane is denoted as small brackets and family of plane is denoted with curly brackets. And here HKL, these are integers which have no common factors between them. Now fourth question, which one of the following pairs of axis lengths ABC and interaxial angles alpha, beta, gamma represent the tetragonal system? So one of the example of tetragonal system is martensite. So if you know, so in case of when they all are equal, it is known as cubic, simple cubic system. So for tetragonal, one axis length will be different. Here it is shown here, tetragonal. In case of tetragonal, your C axis will be different from A and B. So all angles will be 90 degree, and other options here are this orthogonal, and one is tetragonal and trigonal, I guess. A equal to B equal to C and one equal not to 90. Yeah, one is trigonal. So fifth question is, what is terminology representing the movement of block of atoms along certain crystallographic plane and directions? So options are glide, slip, twinning and jog. So what will be the answer? Answer will be slip. And okay, so answer will be slip, and it can be defined as mechanism of plastic deformation along with twinning and climbing. So twinning also and climbing, these all help in plastic deformation. But in case of slip, you'll be having half plane of atoms, which is known as dislocation. Here it is termed as block of atoms, and they move on slip planes in slip direction. So this is definition of slip, so slip fits better here. And in case of twinning, there will be some reorientation of atoms which can be in fraction of atomic distance also. And in case of jogs, they develop by the interaction of dislocations, and these restrict the movement of dislocations. Sixth question. Now, which of the following is a point imperfections? And vacancy, second is interstitial C, third is Frankel imperfection, fourth is Schottky imperfections. And your options are 1, 2 and 2, 3, 2, 3, 4 or all of these. So answer will be all 4, and these can be explained by saying that in case of vacancy, there will be an empty atomic site. So at a particular, in case in a crystal structure, an atomic site will be empty, and in case of interstitial C, atom will occupy an interstitial site. And in case of Frankel defect, there will be formation of vacancy interstitial pair. And in case of Schottky defect, these Frankel and Schottky defect, these are seen in ionic solids. In Schottky, a pair of missing anions and cations from the lattice. It is very similar to vacancy defect, so these all are point defects. So all 4 of these are point defects. Next question is, which one of the following defects is Schottky defect? And options are vacancy defect, compositional defect, interstitial defect and surface defect. And answer will be vacancy defect. So I just defined what is Schottky defect. It is a pair of missing anions and cations. So it is type of vacancy defect. As it is also explained here, like a missing pair of anions and cations from the lattice, so it is vacancy defect. And compositional defect is due to alloying or impurity, so composition change will be there. And examples are substitutional and interstitial defects. And interstitial defect is when an atom other than the parent atom is present in the interstitial site. These interstitial can be tetrahedral voids or octahedral voids. And surface defect is the outermost planes of a material are surface defects, which is a physical boundary of a material. So it will be separating this material from surrounding. Eighth question is Jomini and Quench test is performed to determine. Options are recrystallization temperature of steel, glass transition temperature of a material, hardenability of material, or hardness of steel. So Jomini and Quench test is performed for getting hardenability of steel. Setup is shown here. So in case of this test, we take a specimen with having a specific geometry and specific dimensions. Then we'll be heating it to austenization temperature. Then we use a water jet to cool it, to quench it. So there will be formation of martensite, and somewhere between there will be slow cooling, so there will be pearlite formation also. So we'll be getting depth at which 50% martensite and 50% pearlite is formed. So that depth will be defining what is the hardenability of steel. In this case, then hardness will be measured at various points. So hardness which will be corresponding to 50% martensite and 50% pearlite, that will give us the depth and hardenability. Question number 9. So a common crystal structure for ceramic material is, your options are FCC, BCC, HCP and perovskite. So your answer, what should be the answer? Answer will be perovskite. And this is what perovskite structure looks like. So here at the corner atoms, there will be certain atoms and different atoms will be at the face centers. And at body center, there will be a different atom in cubic cell. Ceramics solidify in complex structures. One of these is perovskite. And a perovskite is any material with a crystal structure following an formula ABX3. X will be oxygen or other elements from that particular column. It was first discovered as the mineral called perovskite, which consists calcium titanium oxide. And BCC, FCC, HCP, these all three, they are common examples of metal crystal structure. Now, 10th question is, which one of the following is an example of Frankel defect? So one chlorium vacancy and one sodium vacancy in NaCl. Another option is one zinc vacancy and one zinc interstitial in zinc oxide. Other option is K at the Na site in NaCl, potassium at sodium site, and none of the options. So in case of Frankel defect, we know that in case of Frankel defect there will be an interstitial and vacancy pair. So answer B should be correct. Now Frankel defect can be defined as formation of vacancy interstitial pair. In it, cation leaves its lattice site and site sits in interstitial site. And in case of chlorine vacancy and sodium vacancy in NaCl is example of Schottky effect. And potassium at Na site in NaCl is also example of Schottky effect. Now we'll be going through some lecture slides. So for understanding atomic bonding and crystal structures, understanding periodic table is necessary. So in case of periodic table, we know that when we go through columns, we see very similarity in their properties. So for a particular column like beryllium, magnesium, calcium, these all will show similar properties. And why is that? Because in a column, valence structure remain the same. Like in outermost shell, they will have similar number of electrons. Like these will have 2, these will have 1 electrons in their outer shell. So when we'll be moving at this side, so we'll be seeing that these will have just 1 electron to lose. So these can easily lose their electron and they will show highly metallic behavior. And when we move in this direction, right hand side, then we'll be seeing that these will have these will have 8 electrons in outermost and these will have 7 electrons. So they will be requiring just 1 electron to fill their outermost shell. So they have tendency to gain electrons. So these will have positivity and these will have electronegativity. And it is written here like readily give up electrons to become positive ions, and cesium is most electropositive. And in this direction, these readily acquire electrons to become negative ions, and fluorine is most electronegative. Now, for understanding the origin of material properties, we require study at the atomic level. So there are interatomic bonds and atomic packing. So how these two atoms are bonded, then how these bonded atoms they are packed in a material. So for interatomic bonds, one of the model is spring-like bonds. So these atoms are held like together and they act like springs by linking one atom to other in a solid state. And atomic packing, this signifies the way in which atoms are packed together. Here number of spring per unit area and angle at which they are pulled. These all define the properties of materials. Now atomic bonding, there are mainly two types of bondings, primary and secondary. In case of primary bonding, these are relatively strong and materials melt between 1000 to 4000 Kelvin. So these will be in solid form. And in case of secondary bonding, these are relatively weak and these materials melt between 100 to 500 Kelvin. So these can be liquid also. Primary bonding, these are mainly covalent, ionic or metallic bonding. And in case of secondary bonding, van der Waals bonding and hydrogen bonding, these are classified in this class. Now first is ionic bonding. It is found in compounds that are composed of both metallic and non-metallic elements. So a part of a compound will be, half part will be metallic and half part will be non-metallic. There will be large difference in electronegativity required, which means bonding occurs between elements situated at the periodic table's horizontal extremities, and it requires electron transfer to achieve stabilized outermost electronic configuration. So there will be some electron transfer and the bonding forces are Coulombic and the attraction between opposite charges will be there. Examples are sodium chloride, AgCl, CaCl, zinc sulfide, calcium fluoride, lithium fluoride, magnesium oxide, alumina. These all will be having ionic bonding. Now the properties. Ionic bonding bonds are non-directional because the magnitude of the bond is equal in all the directions around an ion, and these show higher melting point because there will be large bond energy. So when they will be bonding, there will be release of energy, so they will be highly stable. So this is the energy around 3 to 8 electron volt per atom. Now often hard and brittle materials, these are, yeah. Yes, you want to ask any question, Anandita? Okay, so all we can see that most of salts, they are hard and brittle materials. Do you want to ask any question, Anandita?
నాకు చేద్దాం
Okay, so these are often hard and brittle materials. Ionic solids are good insulators of electricity in their solid state and good conductors of electricity in their molten state. Now moving on to covalent bonding. These have stable electron configurations are obtained by the sharing of electrons. So here two different elements, they will be sharing electrons among them and between adjacent atoms. So these atoms will be situated very near in the periodic table. There won't be any electronegativity difference, will be lower compared to when we see in ionic bonding. Like in case of ionic bonding, these extremities on the horizontal line, these will be forming compounds. Now the covalent bond is directional in nature, means occur between specific atoms and only in the direction between one atom and another that participates in the electron sharing. And the number of covalent bond for a particular atom, it can be given as 8 minus n, where n is number of valence electrons. Like for carbon, we see it is number of valence electrons is 4, and it will have 4 covalent bonds. Example is non-metallic molecules like hydrogen, fluorine and chlorine. These gases, these will be having covalent bonds between them. And molecules containing dissimilar atoms like methane, H2O, HNO3, HF, these will also have covalent bonding. So sharing of atoms will be there. And elemental solids, diamond, silicon, germanium, so these will also show covalent bonding because these have 4 electrons in outer shell, so these tend to share electrons. Solid compounds, gallium arsenide, indium antimonite and silicon carbide, these will also have covalent bonding. Polymers, these also contain secondary bonding also. So in case of polymers, along the chain when we go, so along the chain they will be having covalent bonding, and between different chains will be seeing secondary bonding. Now examples of covalent bonding. So covalent bond formation between two hydrogen atoms making hydrogen molecules. So here one hydrogen atom is there, so it will have one atom in outermost shell and it is proton, so these will be sharing their outermost electrons, molecular electron orbital containing 2 electrons. Covalent bonding in methane molecule. So a carbon atom shares its 4 valence electrons with 4 hydrogen atoms. So here carbon will be sharing 4 electrons. Okay, so hydrogen will be sharing its 1 electron. So in hydrogen outermost it will be 2 electrons, and in carbon there will be 8 electrons. So it will be completing their outermost shell with helping of sharing of electrons. In diamond, so it also has covalent bonding, and diamond has very high thermal conductivity, around 5 times of copper, and it is electrically insulator, and it melts at very high temperature, around 3600 degrees C, and due to presence of tetrahedral geometry and highly directional covalent bonding, and it has no free electrons, and heat conduction is because of lattice vibrations, which is also known as phonons. It is used in applications such as cutting tools, polishing wheels, and precision bearings, etc. Now metallic bonding, it is found in metals and their alloys, and alloys are will be having base as metal, so they will be having a metallic bonding. In metallic materials, they have at most 3 valence electrons, which are not bound to any particular atom in the solid, forming an electron cloud. Now they will be giving their electrons to the electron cloud, and these ion cores will be there, which will be held together with the help of these electrons. So rest non-valence and atomic nuclei form ion cores having a net positive charge, and there is a force of attraction between valence electrons and metal ions, and these free electrons, this cloud, it will act as glue to hold these ion cores together, and the metallic bonding imparts properties such as strength, malleability, ductility, luster, conduction of heat, and electricity. So because these electrons, these are free to move, so these are conductive to electricity and heat. Now moving on to secondary bonding, first one is hydrogen bonding. In this, strong dipole-dipole attraction that involves molecules with OH, NH, or FH. So fluorine, nitrogen, oxygen, they are highly electronegative, and so this hydrogen and oxygen, between them there will be formation of hydrogen bond, and one of the this is hydrogen bonding is one of the reason why water expands upon freezing. So we know that volume of this ice that will be more compared to liquid water. So in solid ice, each water molecule participates in 4 hydrogen bonding. So hydrogen bond keeps molecules apart, thus relatively open structure will be there like this. So hence ice has a lower density than liquid water, and it floats. Now van der Waals bonding, so here it is weak in comparison to primary bonding. So bond energy is 0.1 electron volt, and which we saw in ionic bonding, it is 3 to 8 electron volt per atom, while it is 0.1 electron volt, so it is very weak compared to that, and it occurs to some extent in all materials, but is particularly important in plastics and polymers, and it results from attractive forces between electric dipoles. So if there is dipole formation in some atoms, so between those there will be formation of van der Waals bonding. Now we know the materials can be, main classes of materials will be ceramics, metals, and polymers. So in case of ceramics, the main bonding will be either ionic or covalent, or it can be mixture of both of these also. So these will have very high bond energy, and these will show high melting temperature, large elastic modulus, and small thermal expansion coefficient alpha. In case of metals, these will be having metallic bonding, and this bonding gives them variable bond energy, moderate melting temperature, moderate elastic modulus, and moderate thermal expansion coefficient. And in case of polymers, they will be having covalent bonding along chains, and between chains they will be having secondary bonding. So these will be having directional properties. So in one direction they can have different elastic modulus, and in one direction they can have different, and these will be having secondary bonding will be dominating, and so these will be having low melting temperature, low elastic modulus, and very large thermal expansion coefficient. So these will be expanding more when we heat them compared to ceramics and metals. Ceramics show very less expansion. Now crystallography, which is a study of atomic and molecular structure, and the study of crystal geometry helps to understand how the atom in a material are arranged in order to interpret the relationship between atomic structure and properties of these materials, namely mechanical properties, electrical properties, magnetic properties, optical properties, and metallurgical properties. So in crystallography, we mainly study the relation between these properties and how it is dependent on their particular crystal structure and atomic packing. The common technique that we use for identifying what type of crystal structure is present in material, we use X-ray diffraction. Now solid materials, these can be, depending on the arrangement of the atoms inside them, these can be classified into three types. So these can be either crystalline, polycrystalline, or amorphous. In case of crystalline, they will be having long range ordering between atoms. So there will be an order in which these atoms will be arranged. In case of polycrystalline, it is mixture of these amorphous and crystalline part. In case of amorphous, there won't be any long range ordering. So in case of polycrystalline, various crystallites, small crystals will be there, and between them there will be boundaries. So these boundaries will be amorphous in nature. Crystalline solid, in case of these, long range structure exists in which atoms are arranged into unit cells, and the unit cells repeat in a regular orderly pattern, forming a 3D lattice. So in this, if a material is crystalline, like in case of single crystal, it will be showing directional properties, meaning anisotropic nature. So in particular, like in this direction, it will be showing different strength, and in this direction it will be showing different strength. So at a particular angle or at a particular direction, it will show different properties. These also have sharp melting point, and examples are gold, silver, aluminium, all metals. These solidify in crystalline structure. Now polycrystalline solids, these are made up of an aggregate of many small single crystals, also called crystallites or grains. So these are different grains which will be having different orientation, and at particular grain boundary this orientation will change. Now across grain boundary the orientation of crystal changes, and the grains are usually 100 nanometer to 100 micron in diameter. Polycrystalline materials have a high degree of order over many atomic or molecular dimensions. So these materials will have ordering, and polycrystals with grains that are less than 10 nanometer in diameter. So these will be called nanocrystalline. Most engineering materials are polycrystalline because of the conditions that we form our materials in. These always solidify in form of polycrystalline, and properties may not vary with direction, because different direction orientation, these act as isotropic materials. Now example, common steel and polycrystalline. So if grains are textured when we roll steel, or if we recrystallize it, it can become textured. So then it acts as, so all grains, they will be oriented in particular directions. So it will show anisotropic properties. And if grains are random, then it acts as isotropic properties. It show isotropic properties. Now for the single crystal, it will have only one grain. There won't be any grain boundaries. It is formed by uniform cooling of liquid material. So if we cool it slowly, or by if we control these solidification parameters, then we can form single crystal, and we have a high degree of order throughout the entire volume of material. It is useful for applications where grain boundaries are harmful. So for example, if high temperature deformation or creep resistance, as creep takes place by grain boundary sliding. So if there are presence of these grain boundaries, along these grain boundaries, atoms can diffuse easily. So along these grain boundaries, atoms can diffuse easily, and so it causes creep of material. So we want to reduce number of these grain boundaries. So for this, we want to make single crystal. So single crystal turbine blades, nickel based superalloy gas turbine blades, these withstand creep at high temperature due to lack of grain boundaries. And other uses of single crystal is in case of making diamond and semiconductors also. We want to make them single crystal. Now amorphous solid. The atoms or molecules are arranged in a irregular manner, and there won't be any periodic packing. So when there is no long range order, these will be amorphous solids, and there won't be no directional properties will be there. It acts as isotropic substance, and it occurs for complex structures. So if, for example, if we have more elements, like more than 3 4 elements in a system, so it is more likely that it will solidify in form of a amorphous solid. And also if we are rapidly cooling a metal also, so it will solidify in form of amorphous solid, which is known as metallic glasses. So example of amorphous solid is glass, plastic, rubber, etc. Here it is silica structure. When it is amorphous, its structure looks like this, where smaller atoms are silicon atoms, which are bonded with 3 other oxygen atoms. Now unit cell. Unit cell is the smallest block or geometrical figure from which the crystal is built up by repetition in 3 dimensions. So when we take a material and for repetition part, if we can repeat it and we can reach at the crystal structure again, so that will be your unit cell. It is the fundamental grouping of particles which are repeating entities, and the unit cell is the basic structural unit or building block of the crystal structure. A crystalline solid can be constructed from a unit cell plus translation operators. So, for example, if this is unit cell, if we are translating it in x direction, so we'll be getting 1D lattice. So, if we are translating in y direction, we'll be getting a 2D lattice, and if we are translating it in z direction also, you'll be getting a 3D lattice. Now, for the crystal system, we need to understand two definitions. First is lattice and basis. So, lattice is in space. So, when we will be putting some bases, meaning some atoms in it, that will be forming our crystal structure. So, lattice is just a mathematical entity. So, lattice is array of points in space in which every point has an identical environment. So, this atom will have similar type of atoms surrounding it what this atom will have at particular distance. So, and basis is single atom or a group of atoms. So, it can be a molecule also. So group of atoms identical in composition and orientation in space. So this will be a lattice which is in space. So when we'll be putting some atoms on these lattice points, we'll be getting a crystal structure. Now there are mainly 7 crystal systems: cubic, hexagonal, tetragonal, rhombohedral, orthorhombic, monoclinic and triclinic. In case of cubic, so these all axial lengths will be equal and all the angles will be 90 degree. In case of hexagonal, AB will be equal and C won't be equal, so C will be this direction, and ABC, A alpha and beta will be 90 degree and one angle will be 120. In case of tetragonal, there will be one this C will won't be equal to A and B. In case of trigonal, this angle won't be equal. So in orthorhombic, these axial lengths won't be equal, but all angles will be 90 degree. Monoclinic and triclinic will be most asymmetric type of structure, because on all axial lengths and all angles they won't be equal. Now some of the crystal structures that are studied most. First one is simple cubic. In case of simple cubic, we'll be having a cube and at the corners we'll be having atoms. So in this, the unit cell consists of 8 corners atoms, and all these corner atoms contribute only one effective atom for the lattice, because this corner atom will be shared with 8 other such unit cells. So it will be 1/8 in this unit. So 1/8 multiplied by 8 corners. So it will be giving us effective number 1. And when we calculate packing fraction, in case of packing fraction, we need to firstly take this volume of atom, effective number of atoms, divided by this volume of entire unit cell. So here we are taking number of atoms is effective is 1 multiplied by 1 atom has volume. We are taking here sphere, so 4/3 pi r cube. Okay, so pi r cube, 4 by 3 pi r cube is volume of this atom. So we are multiplying it with the effective number of atoms divided by a cube. A cube is volume of your this unit cell. So for simple cubic, when simple cubic through this, we can say that a is equals to 2r. So on a will be keeping 2r, and when we'll be calculating it, it will be 0.52 for simple cubic. So and coordination number will be the number of atoms immediately surrounding a central atom in a crystal. So for example, this atom, if we take this atom, it will be having immediate this atom, and similarly one atom will be in this direction, one will be in this direction, 4 atoms in this plane, and one atom this one, and one atom at the top of it. So 6 atoms will be nearest neighbors for this atom. So, and it is rare due to poor packing, so it is only found in polonium. Now another crystal structure is body centered cubic. In it there will be one extra atom at the body center and other atoms will be at the corner. So when we'll be calculating, it will be similar to simple cubic plus one atom at the body center, which won't be shared with other unit cells. So when we'll be calculating packing fraction, we'll be just multiplying it with 2, and a will be different here also. So by using Pythagoras theorem, you can calculate that this 4r will be equal to root 3a. So when we'll be putting this in formula, we'll be getting packing fraction as 0.68. Now BCC structure has 8 corner atoms and 1 body center atom. So the coordination number will be 8. So like we can see here, for this atom, nearest neighbors will be all these atoms which are at the corners, and 8 corners, so it will be having coordination number 8. Now examples of body centered crystal structure are in chromium, iron at lower temperatures, not at higher temperatures, it will be in FCC form, and molybdenum, potassium, sodium, tantalum, vanadium, these all solidify in BCC structure. Now one of the most common crystal structure is face centered cubic. In this, atoms will be sitting at face centers, and these face center, this face is shared with one more unit cell. So half will be inside this unit cell, half will be in another unit cell. So we'll be multiplying half to 6 because there are 6 faces. So the total number of atoms will be 4. And when we'll be calculating packing fraction, we'll be multiplying it with 4 number of atoms, and this is volume of one atom. And now we'll be dividing it with a cube, and here using same Pythagoras theorem, you can calculate that root 3a will be equal to 4r. So your packing fraction will be 0.74. And in FCC crystal structure, it has 8 corner atoms, and each face will be having one center atom, and coordination number will be 12. So coordination number, as we saw in initial questions, coordination number, yeah, here. So for FCC, we'll be seeing at this particular, for this particular atom, 6 atoms will be surrounding this in one plane, and top and bottom planes will be having 3 extra atoms. So it will be having 12 coordination number, and similarly for HCP also will be having 12 coordination number. And examples are aluminium, copper, gold, silver, lead, nickel, platinum. These all are very ductile in nature, and these all are FCC structure. Now, hexagonal centered cubic. This will have atoms at these corners, and one atom this will be shared with 6 other unit cells. So we'll be taking it 1/6 multiplied by 12, because 1 2 3 these will be 6 6 and 6, this will be 12 atoms, and 2 multiplied by half. These atoms which will be at the center of these faces, these will be shared with 2 unit cells, so we'll be multiplying it with half, and 3 atoms will be inside this unit cell, they won't be shared, so total effective number will be 6. So packing fraction similarly we can calculate, and it will be similar to FCC, so 0.74. And stacking sequence will be AB. So, and the center atom is not shared by any other unit cells, and coordination number will be 12. Examples are magnesium, cobalt, zirconium, titanium, zinc, cadmium, beryllium, etc. These are most common crystal structures, HCP and FCC. Now, moving on to Miller indices. So these are the designations of the planes and directions in unit cell, and the number of indices will match with the dimension of the lattice or the crystal. Now the example of in 3D, the unit cell has 3 indices, namely H, K, L. They won't be having any comma in between, and if there is comma, it is for denoting coordination. So it represent a point, but no comma is used while representing indices. So these are various brackets that I used. Small bracket is used for individual plane. Curly bracket is used for family of planes. So like in family 100 there will be other planes also. And square bracket is used for individual direction, and triangular bracket is used for family of directions. Now for Miller indices of a plane, in case of plane, firstly we'll be choosing a origin, and like if this plane is given, so firstly we'll be giving them A, B, C, and if it is cutting on x direction at 1, and intercepts are either 1 1 1 here, so firstly we'll be taking reciprocal. In case of planes we'll be taking reciprocals, so 1 by A, so it will be A will be 1, B will be 1, C will be 1, so reciprocals will again will be 1 1 1. And if it is in terms of fraction or it is in multiple, so we can either divide with same number or we can multiply with same number to eliminate fractions. And then we'll be putting bar, like A bar for if integer is negative, and we'll be placing round bracket around indices to get plane. In case of Miller indices of a direction, so in this case in direction we can shift our origin. So if we are shifting our origin to here, then we'll be labeling it O dash, and the new axis will be x dash, y dash and z dash. So we'll be finding coordinates from tail at O dash to the head of direction, and we'll be reducing multiples, eliminate fractions similar to previous, and we'll be using bar for negative, and we'll be using square brackets here. So like this direction is going in x dash direction, it is moving 1, in so in y direction it is moving in opposite direction, so it will be minus direction, and z direction it is moving positive, so it will be 1 minus 1 and 1. In case of now crystal defects. So in crystal structure there can be defects also. So any deviation from a crystal's completely ordered arrangement of constituent particles is called a defect or imperfection. So the properties of material are influenced by the presence of imperfections, and mechanical properties of pure metal change significantly when metals are alloyed. Now we can classify these defects in four classes. So these can be either zero dimensional, one dimensional, two dimensional, or three dimensional. In case of zero dimensional, so it can be vacancy defect, interstitial defect, substitutional defect, Frankel defect, or Schottky defect. These last two are found in ionic solids. And 1D, these can be edge dislocation, screw dislocation, or mixed dislocation. For 2D, these can either be grain boundaries, twin boundaries, or free surface. In case of 3D, these will be voids or cracks. Now, very important defect is vacancy defect. So these are the empty atomic sites. So when an atom is missing from its regular lattice site like this, then it is called a vacancy. There it is impossible to create a material free from vacancy defects. So these vacancy defects are always found in materials, and presence of vacancies increase the entropy or disorder in the crystal, and these decrease the density of substance because there is no atom is missing, so it will be reducing density. Now the concentration of vacancy increases with, we can either increase temperature. If we are increasing temperature, then this material will have more number of vacancies, and by decreasing activation energy. So this is specified for particular materials. So depending on material, we can see that at a particular temperature it can have different number of vacancies. So the energy required for the formation of vacancies, it depends on melting temperature. Now equilibrium vacancy concentration xv can be given as exponential of minus qv, which is activation energy, divided by kb, which is Boltzmann constant, and T is temperature. So these define what is the vacancy, what is equilibrium vacancy that is present there, because without equilibrium also non-equilibrium methods also can be used to induce vacancies inside material, like if we can quench material from very high temperature to very cool temperature, so that can introduce high number of vacancies inside it, or by using irradiation and other methods like plastic deformation also we can introduce vacancies in material. Now another crystal defect, very important crystal defect, is grain boundaries. So grain boundary, in next week you will be studying about how grain boundaries are used for increasing strength of material. So these are the boundaries that separate two grains or crystals which will be having different crystallographic orientation. Like these materials, these have orientation in this direction while these have in this direction. So this is misalignment, angle of misalignment. So by measuring this angle, we can know whether it is a high angle grain boundary or small angle grain boundary. So the atoms near boundaries, they are slightly disordered because there will be some compressive or tensile stresses related to that, some strains will be there, and these have higher energy than those within the grains. So in crystalline part of material, if atom is present here, it will be have it will have less disorder. In general, a grain boundary has 5 degrees of freedom, and if we need 3 degree of freedom to specify the orientation of one grain with respect to the other, and 2 degree of freedom to specify the orientation of boundary with respect to one of the grains. So okay, this is all. So now you can ask any question, any queries if you have. I will be present here till 5 o'clock, so if you have any queries, you can ask.
Hello,
Yes,
madam.
yes,
There was one question in a second assignment.
okay,
It's about what type of crystal defect is characterized by a missing atom in the lattice.
yeah,
So four options were given.
okay,
These four options, that is Schottky's defect, Frenkel defect, interstitial defect.
yeah,
Okay. So even in the Schottky defect, there is a missing atom, or interstitial defect, there is a missing atom.
yeah.
But the answer is taken as a Frenkel defect. How it is? Can you elaborate on that?
What was the question again? Can you repeat the exact question?
Uh, which type of crystal defect
Yeah,
is characterized by a missing atom in the crystal lattice?
missing atom should be vacancy.
Yeah,
Okay, there will be vacancy interstitial pair, then it will be Frankel.
interstitial.
If there is a pair of vacancy and interstitial, like if it is ionic solid, right?
Yeah,
In ionic, like if your zinc is going from its original position to interstitial,
okay.
then it will be Frankel. So if there were, was there vacancy also in options?
The question is like this: which type of crystal defect is characterized by a missing atom in the crystal lattice?
Okay.
And the options which were given, that is Schottky defect, Frenkel defect, interstitial defect, and grain boundary defect.
Okay, so out of these short key should be there. Like in short key, both atoms like ion, anion and cation
Yes,
will be absent.
and they are not present. Yes. So the correct answer is a Frenkel defect is given.
Okay, so in portal you can raise a query
Okay, okay.
whether
Thank
that
you.
should be correct answer. Yeah.
Okay.
Okay.
Thank you.
Okay.
Even madam,
Yes.
even in this uh, uh, ceramic material,
Yeah.
it is mentioned that it's a crystal structure is SCP crystal structure, but the answer is perovskite.
Yeah.
Is it?
Perovskite will be answer. Correct answer.
Okay. Thank you. Thank you very much.
Yeah, this is the crystal structure of perovskite. So because in ceramics these are complex structures.
Okay. Okay.
Okay.
Thank you. Thank you.
Yes, Gaurav, do you have any query?